Good. Okay, so recording has started. Um, okay, it's 1 o'clock on the West Coast. Welcome everybody. Um, this is the first of 3 sessions of the FIRO Technical Workshop, spanning today and tomorrow. Um, I'm Joe Forbis. I'm with ERDIC. I'm the Water Management Integration Lead there. Um, and I want to welcome you all to this first inaugural FIRO Technical Workshop, I suppose. And thanks for being accommodating and adapting to um, uh, initially having a planned in-person meeting and helping us and supporting us and transitioning us to this all virtual one to accommodate the travel hiccups and obstacles that a lot of folks that we wanted to participate were going to face in trying to make an in-person one happen. Um, I want to start off by giving a quick little background on like what this is for. So we've found, now that the FIRO program and all these various FIRO pilot projects and FIRO efforts have been underway for for a certain number of years now, that the FIRO annual workshop, typically in August in Southern California, has been really helpful in like touching on certain subjects and introducing them in at a high level. But we are seeing that now that we're really in a good implementation sort of phase of how do these FIRO ideas go from these pilot projects into a reality in the form of being included in potential water control manual updates, is that the annual workshop just isn't long enough to allow us to delve deeper into a lot of these topics. And so with multiple pilot projects underway, the screening process being rolled out, and all these other things, some of us thought it would be useful for us to get all these folks that have been supporting various FIRO efforts to different degrees, folks at Corps of Engineers districts, water agency partners, CW3E, of course, and various consultants that are supporting us in the execution of the FIRO program, to share what's been going on in more detail and looking more at the technical side of things for FIRO viability assessments, and how that interplays with and overlaps with and can help support water control manual updates. So we have a few almost primary focus areas that between the 3 sessions we're going to be looking at over this afternoon and tomorrow. We're going to be doing some more in-depth talks on the integration of forecasts and observations. We're going to be talking about viability assessments and water control manual updates. And then we're going to be talking about decision support systems and tools, whether it be the HEC products like SWIMS and WATT, or various water management dashboard efforts such as what Aquaveo has been working on. Some of you may know bits and pieces of those things. We're hoping that we can get everyone up to speed on all of those things, and that will help us be more effective and efficient with current and future FIRO work. Julie, is there anything that you wanted to add to kind of set the stage for this first session?
No, I guess one thing is we want this to be a learning experience and a community together, that we're all learning together. And so we've shortened the time, and obviously this would be nice to do in person, but please use the chat, ask questions, that given some time constraints, maybe that's the best way, but think about those questions, be ready for them. So we all learn together, and that's really the essence of this. So thanks, Joe. And thanks for initiating all of this.
Oh, sure. Yeah. I think in the leading up to in the planning, I think Julie did a whole lot of initiating and I just did responding. So Julie deserves a lot of credit for getting this up off the ground. Yes, I'll reiterate what she said. Please, whether it be in the chat, you can even use the raise your hand feature as well. But this isn't just a report out session. This is we want to get conversation and discussion and questions flowing as well. So if you want one of the presenters or speakers or whatever to expand more on something, we have allocated time in the agenda to allow for those sorts of discussions and conversations to happen. So please, if anything comes up, don't be afraid to interject and contribute to the discussion. That would be fantastic. I think I said at the beginning, I'll say it again, we are recording this, so then that way, if you miss anything during this session, or if there's people that couldn't come to this first session, that we'll have it available for people to access afterwards. And for today's session, specifically for session 1 today, we're going to be looking at 2 main topic areas: the integration of forecasts and observations information. Ava, Chad, Taylor, Brett, and Patrick will be walking us through that item on the agenda. And then following that, I'll give a short presentation on how viability assessments can support water control manual updates. Then we'll wrap up, and we got some more fun stuff on the docket for tomorrow, but we'll roll right into the integration of forecasts and observations information. So Julie, I don't know if you were facilitating that one specifically, or if I just call on Ava right now to say, go ahead and get us started, but that's the next thing that we're going to do.
Great, thanks, Joe. I'll just say real quickly, is we're breaking this up kind of into 2 sections, talking about how observations and the value of observations. And the second session is or part of this session, we'll be looking at forecast. And so there, you'll hear from some people twice, thinking about both the observations and the forecast. So with that, I'll turn it over to Ava Cooper, who's a researcher here at CW3 and leads a lot of the observation work that we do for FIRO. So Ava, it's all you.
All right, I think I'm sharing my screen. Let me know if it's not showing up though.
Yep, we can see it. Thanks.
Awesome. Thanks, Julie. Thanks, Joe. As Julie said, I'm a data analyst with the CW3E field team. So I'll be kicking off our discussion of integration of forecasts and observations information, specifically the CW3E observations portion. So throughout this, we're going to be highlighting a specific event from early February of this year in the Russian River. But starting out more generally, forecast-informed reservoir operations supports a lot of different observations through our monitoring networks. We have a lot of continuous near real-time stations, and then we also do storm-based sampling with radiosondes and streamflow. So the map on the right shows all of our current FIRO stations in our California and Washington FIRO watersheds, and then also highlights some of the watersheds where we will launch radiosondes or do streamflow sampling for specific atmospheric rivers. For near real-time continuous stations, we have a couple of different types, including streamflow, surface met plus soil, which has a standard suite of surface met sensors and includes precipitation. And then we have some more specialized station types that include our distromets and radmets that have distrometers to measure precipitation phase at the surface. And then the radmets have a micro rain radar to detect snow level in the atmosphere. So many of these stations are telemetered, so the data are available in near real time on our website and also through our data share linked here. And then we push those data to a variety of partner websites, including CDEC, NOAA PSL, and MESOS/Synoptic data. So those data are available to partners to reference in real time. Specific to the river forecast centers, we also get these telemetered stations, something called an NWSLI. This is an ID issued by the National Weather Service that allows for inclusion of these station data in different products. So for a precipitation station, allows for its inclusion in products like the quantitative precipitation estimates. So over the course of FIRO, CW3E has added about 20 stations with NWSLIs in California, and then all 3 of those stations in Washington also have these IDs. Specifically in the Russian River, we added a lot of stations in 2017 through the first FIRO pilot project in Lake Mendocino. So this map on the right shows the existing QPE stations in teal, and then stations added by Lake Mendocino FIRO or subsequent efforts in orange, as well as some of our streamflow sites in those square markers. The screen grab on the left shows those stations and the gridded QPE for the entire month of February from the RFC website. This is accumulated precipitation for the month of February. So we can see the detail added by those stations from FIRO Lake Mendocino and some additional resolution in this precipitation hotspot near Venado that we'll talk about in a bit. During this early February event, these stations were providing near real-time data at a 15-minute resolution to CDEC and then the RFC. But if you were to go to our website and our observations pages, we have a 48-hour window showing the last 48 hours of data from any given station. So if you logged on there and looked at Boys Creek Canyon on the 5th of February, you would see this plot showing the different surface MET sensors, accumulated precipitation, soil moisture, and soil temperature. And we see that for this 48-hour window, we accumulated 4.5 inches of precipitation at Boys Creek Canyon. In total for this event, precipitation ranged from 4.2 inches to 7.5 inches for the CW3E stations in Lake Mendocino. So you kind of get an idea of the detail added by these stations in the Lake Mendocino watershed. We also have our streamflow stations throughout the Lake Mendocino area. These are collecting stage and now discharge in near real time and providing that to CDEC as well. So this example is from Cold Creek at Highway 20, and we observed a maximum of 588 CFS during this event at Cold Creek. So while y'all are hopefully able to reference these data in real time on our website, we will actually be out there collecting even more data on the field team. So during atmospheric rivers, we will go out and do radiosonde sampling for the Russian that is from Bodega Bay, California. We launched a total of 40 radiosondes for this particular event. So these are collecting air temperature, relative humidity, pressure, wind speed, and direction as they ascend and descend in the atmosphere. Those data are then uploaded to the global telecommunications system, so they're available for assimilation into various forecasts and models. We'll also go out and collect manual discharge measurements at our stream sites to build out the higher flow end of those rating curves to ensure that the discharge, like the near real-time discharge data, are reliable. All of our FIRO work has also allowed for a lot of good collaboration with partners and discussions of observations throughout the watersheds that we're working in. So during the FIRO Lake Sonoma or FIRO Lake Mendocino and subsequent process, we learned about this precipitation hotspot near Venado, California, where historically there was one station used for QPE at Venado, and the gauge itself had the occasional issue of over-reading precipitation. So with DWR and Sonoma Water, that issue was resolved in 2021. And through some additional coordination, CW3E and DWR added a station at Austin Creek to help us further resolve that precipitation hotspot. In total, for that early February event, Venado observed 13.7 inches of precipitation and Austin Creek observed 9.2. So definitely a lot of rain in that hotspot. FIRO also supports a lot of other observation types, not necessarily relevant to that event in the Russian, but relevant to our snowier watersheds in the Sierra Nevada and Cascades. This includes our snow level radars to measure snow level in the atmosphere and our distrometers to measure precipitation phase at the surface to give us a better idea of where the rain snow transition elevation might be in these watersheds and the implications for runoff from those. Links to those data are in the bottom corner, but I think that's about all the time that I have, and I'll hand it off to our next presenter. Happy to answer questions though in our discussion section.
Thanks so much, Ava. Brett, do you want to go ahead and talk about how observations are used at the CNRFC?
Sure. All right. Hopefully everyone can see this. Yeah, so observations, meteorological observations obviously are important for streamflow forecasting. You know, the meteorological inputs we bring into our hydro models are temperature, precipitation, and freezing level to define precip type. I'm just going to focus on precipitation observation networks and how we use them. The temperature and freezing level are really just automated products that come into us. The precipitation estimates are a more manual process that we do at the CNRFC. And so we have hydrologists that basically look at 6-hour time periods, so 4 periods throughout a 24-hour period, looking at precipitation totals and quality controlling them. And ultimately what we do with all those point values is we estimate in the end as a mean area of precipitation for that watersheds, because since we model things in a lumped fashion. So our precip estimates are strictly from gauge data. There are other, tools out there like radar and MRMS, which does take into account some radar, but we use them more in a qualitative sense. Sometimes if we have light precipitation, we're not totally sure if that value was, a bad value or if there really was something there. Sometimes the radar or even looking at MRMS as another data set can help us determine whether we should be setting something a gauge bad or good when we're going through the QC process, typically when it's more sort of a lighter precipitation amount. Okay. The inputs, it's important to know that, we bring in quite a few precipitation gauges throughout the CNRFC domain, covering most of California, Nevada, and a little bit of Oregon. So 2,500 gauges, probably a little bit more. This slide was from a year ago, so we might actually have a bit more now. And they come from a variety of sources, USGS, California DRER. I should mention CP3E, they're not on this list, but the core, it's a lot of partner agencies that we rely on for those real-time precipitation estimates. Alert networks, Snowtel, etc. But we only probably bring in maybe half of those gauges to our precipitation estimate process where we're QCing them. One thing that's important about, I guess, hydro model and modeling in general is that, when you calibrate a hydro model to inputs, and in this case, observed precipitation, the network that you use to generate those mean area precipitation estimates for calibration, you'd like that to be as consistent as possible in the operational environment, because you don't want to introduce biases. So even if you had, 50 gauges in a watershed that came online tomorrow and gave you a real good estimate of what realistically is going on out there in terms of the rainfall distribution, we may not want to do it just because it could be introducing a bias into the modeling that that was built into the calibration when we calibrate the model to a different network of gauges. So we have to be cautious about adding new gauges to our precipitation estimates. So these are point gauges, point locations, and so we spatially distribute that using Prism to get into a gridded format, and then from the gridded format, that's where the mean area precipitation estimates are done to get it to the watershed level. So that's essentially, in a nutshell, how we use precipitation gauges to inform the hydro modeling. We also bring in stream gauges, and we quality control those as well manually. And we look at a variety of gauges, rivers, reservoir information, etc. I throw rating curves in there too. It's not really a gauge, but it is something that we do ingest every day and get the latest rating curve updates that translates flow to stage, and they do change. And so that is another source of information that we use when estimating observed stages or observed flow stage into the forecast period. Here's a screen capture of some images from our hydro modeling, hydro network stream gauges. So on the upper left, this is inflow. So obviously inflows are noisy, they bounce around. So we have to be cognizant of that and always sort of take out ones that we think are really bad. We bring in releases, observed releases from the reservoirs, and we also incorporate the forecasts of the reservoirs through our forecast coordinated operations or framework. Pool elevations are important too. A lot of times we're calculating inflows given the reservoir release and a pool elevation using storage elevation curves. So that all needs to be QC'd in the locations where we're actually calculating inflow and not relying on the operating agency to give us the inflow. And also the stream gauges themselves on the rivers. So that usually is done at the same time. One forecaster is usually QCing the river gauges at the same time the other forecaster on shift is doing the precipitation QCing, and they both get done approximately at the same time. And once all that's done, it gets fed into our CHIPS modeling and is used as inputs into the hydro modeling. The precip is, and then the stream gauges are used to really understand how the model is performing in the past. So this is an example of for a screen capture from our CHIPS modeling for a location in the East Sierra that I took just yesterday. So there's snow melt going on there. To the left of that vertical red line are the observations. So those red dots are observations at the gauge. And the green is what the model is simulating. So you can see a diurnal signal, there's melt going on. But you can see the green line is a little bit offset, that's shifted from what actually was happening from what the red dots are showing. And so, we can use those streamflow observations to help inform the forecaster on how they might want to tweak the model to better line that up and ultimately get a better forecast in the future. So the next slide is what I did is I made a change to the unit hydrograph, and so was able to get a better match between the observed and the model. And so now I have more confidence that going forward that the diurnal signal is going to better emulate what's currently going on in the watershed. So that the dashed purple line is what it was looking like before I made the change. And the sort of that greenish, orangish line is what now looks like the forecast based on the changes I made, which were informed by the streamflow observations. So that's how the observations in the streamflow can help in the forecasting process. So I'll leave it there. Hopefully I'm not over on time.
You did great, Brett. Thank you. We actually have a little bit of extra time. So after we finish the obs section, have your questions handy and we can answer some of those or tackle some of those before going on to the forecasting section. Patrick, do you want to talk about as operator how you use observations in your work?
Sure. Just doing a quick sound check. Can you hear me okay?
Sounds great.
Yeah, so in terms of how I have used the observations as an operator, largely it's been to actually check it against the forecast and use that as kind of a starting point for potential discussions with the RFC or other experts in meteorology, just to get a better idea of what goes into these products and whether or not I'm understanding those inputs and whether or not there are certain events that are, harder to forecast and so forth. And that kind of helps, my thinking and decision making in the future. I'll give kind of an example of, I guess, some of that verification that I would have done earlier this year. So here, an example is, me checking the QPF for, this was early February, 5 days out, just trying to see, what, if any, difference there was in the forecast versus the observed. And here you can see 5 days out from the event, I think in the beginning of February, there was some difference in that forecasted precipitation versus the observed. And also verify stream flow. So I'll look at downstream locations, I'll look at reservoir inflow. And here is another same time period kind of example showing that the forecasted inflow was a little bit less than the observed. So this is a type of observation that I'll probably take, and at some point in time, when I have time and the RFC has time, I might ask them some questions about, why was there a difference in this particular period? Was it a challenge in the QPF? Was it something else? Was it the event that occurred at that time? That's the type of thing that I would like to do as an operator, is just to interface with the people who provide these products and learn more about what goes into it. I think that type of interaction actually had some good benefits already. I know a couple of water years ago, I had some concerns with some of the forecasts that we were getting in the Alameda Creek watershed, a reservoir that I helped manage with the state. Resulting from that, it actually resulted in the RFC redelineating, I think, that subbasin in that watershed. So it was good to have that interaction, and kind of led to a tangible result. But that's how we've used the observations here in San Francisco District. I'm sure the other water managers may use it differently, but that's just an example of how we've done it here in San Francisco.
Great. Thank you. Any questions from the group about the observations? Yes, I can plant one, since I know we didn't have a lot of time to discuss it, and Ava, we just touched on it. But for the snow impacted watersheds, can you speak a little bit more about how knowing phase type could be helpful, and maybe even some of the more novel observations, like the understanding the cold content and how that could be relevant for stream flow and runoff?
Sure. So the sort of snow-based instrumentation cover a couple of different, I guess, areas of concern. So starting with like the micro rain radars to measure snow level in the atmosphere, that gives us an idea of where the rain snow transition elevation might be in a given watershed. So with that, we're starting to think about where are we accumulating rain versus snow. If that rain snow elevation is relatively low and there's a large antecedent snowpack, then we're looking at potential rain on snow events, for example. We then have the distrometers measuring precipitation phase, so that provides some information about what we're actually observing at the surface at different elevations. So that can help sort of validate what we're seeing from the micro rain radars and better resolve where we might see rain versus snow accumulation. And then on top of that, we have spun up some more experimental, I guess, observations, or just like very point specific observations, like snowpack temperature, to get a better idea of snowpack cold content, which tells us a lot about susceptibility to melt. And Kyle, you have your hand up.
Hi, actually, this is Sarah. And I think I'm trying to parse out for the observations that you were talking about and the presentation about using them in the hydrologic modeling. I'm trying to parse out the observations that already existed, from RFC work versus new ones that CW3E put in place, and how those maybe were used. I assume they're being used to improve your overall product, but then what will happen to those new gauges as you get further into implementation?
Our plan when we add gauges to a given watershed is to continue the operations and maintenance of those gauges for as long as possible. So the FIRO implementation phase includes operations and maintenance of those gauges. So our intention is to, as long as we have funding, to keep those running. Does that answer your question?
Yeah. So as long as you have funding, you would keep operating those gauges. Okay. And then that includes the stream gauges as well?
Yes, all gauges that we deploy.
I see there was a question in the chat from Dave Curtis about the potential impacts on gauge maintenance given federal budget and personnel cuts. Oh, Carrie responded that it's if only we had a crystal ball, I think is the essence of the answer to know entirely.
Pretty much. We just there's still too much uncertainty right now. Who knows? There's the dust has yet to settle on all the budget cuts and personnel cuts. So it's a scary prospect, Dave. Going forward, we don't know. I've heard some dire things. I've heard some less dire things. So just going to have to stay flexible and nimble if we can.
Yeah, I would say I think we're in the world now of, probabilistic messaging and ensemble forecasting and uncertainty, and that's great. But the whole federal budget and what's going on is a whole nother level of uncertainty that, like Carrie said, there's a lot of unknowns that we're having to deal with right now. So not a whole lot of answers.
Yeah. Hopefully everything won't break before they decide to try and that they need to fix it, but we'll just have to see.
So we would have time for one more question, but if not, we can move forward to the forecasting part of this presentation or section. Hearing and seeing none, Chad, I will go ahead and turn it over to you.
Thanks, Julie. Just working on getting the screen share going. Look good?
Chad, I can see it fine and it looks good. I think there still may be a little bit of a delay similar to, so just maybe pause when you switch slides before you start talking to give it a chance to catch up.
Yeah, it sounds good. Hopefully it's not too bad. I don't know what the deal is today, but of course it's happening today. Yeah, so I'm going to talk about the integration of forecast information into the FIRO process, and something that I could probably talk about for 2 hours, but I'll try to keep this brief and constructive. So really, when making a forecast, if this wants to change slides, there we go. We good? All right.
Yep.
So really, when making a forecast process or making a forecast, it's kind of like generating a story or building a story, and every event is different. So it takes some interpretation and really digging deep and identifying where the uncertainty lies, why there is uncertainty, and then how to adjust a forecast to really be as beneficial as possible, whether it's just communication to a specific user or it's to make an RFC hydrologic forecast. So it kind of starts with identifying those differences, and I typically start with the AR characteristics, and then taking a step further and identifying the reasons for those differences, whether it be a meteorological reason, looking at upper level information, or stepping deeper into the ensembles, maybe starting with the deterministic forecasts. There's large differences, but bringing in ensembles will help into kind of identify that the deterministic might be a little bit outside of the ensemble spread, or at the higher end or lower end. And then to take it a step further, it usually leads to what role do these differences play in the precipitation forecast. Taking all of that meteorological information and atmospheric river information and identifying why some models might be predicting higher precipitation over one location versus another, where that uncertainty might be. Maybe the models aren't going to handle a specific event well, just because there might be a mesoscale frontal wave, and that type of information will be worked into a precipitation forecast. And then to kind of finish things off, it culminates into what story you want to tell, whether it's giving a briefing and talking to some of the water managers or operators, or making the CNRFC HAS QPF and adjusting things where you see fit, and then that HAS QPF gets passed to the hydrologist within the RFC. So focusing kind of on the early February event from this past year, when making a forecast, my day usually starts with the AR landfall tool. It is probably the most popular product on our website. It allows in a clear and concise way to identify if there is activity in a forecast out to 16 days and or what some of the uncertainty is within a given event. If you're unfamiliar with the landfall tool, it's just a probability of atmospheric river conditions along the U.S. West Coast and or foothills and or inland out to 16 days using the GEFS, the EC, the European ensemble system, and even the West Wharf. But looking at the early February event, we are already in the window where probabilities were high for AR activity somewhere along the U.S. West Coast, but just starting here allows you to start picking up on those differences in the forecast, where at this particular moment in time, the European model is forecasting a much longer duration event over Northern California, which ended up being what happened. But there's also characteristics within that blob that you can kind of parse out and then kind of take the next step for your forecast. And if we look at the European forecast at the bottom, there's not only is it a longer duration event, but the probabilities kind of shift upwards or northwards from initial landfall on the 1st and 2nd of February, and then kind of swing back south, which is initially telling me that there is some form of a mesoscale frontal wave or waviness within the atmospheric river as it's making landfall, and there's likely going to be uncertainty around that location, especially over the north and south periphery of the atmospheric river. And I'll take the next step further to see what that looks like in terms of the precipitation. But then I also like to bring in the deterministic plan view maps to get an overall sense of what the evolution of the atmospheric river is and how the European and EC differ there as well, just so it kind of tells more of the story as I'm starting to dive deeper into the precipitation forecast. During the forecast that was initialized in the morning of the 29th of January, looking at the integrated vapor transport or the moisture transport forecast from the EC and the GFS, we were seeing large differences in how quickly the GFS was pushing things southward, leading to a shorter duration event over far northern California, longer duration over the central portion of the state. And that was leading to higher precipitation accumulations over the central Sierra versus the EC over far northern California. It's also important to consider ensembles. If we're just looking at the GFS versus the EC deterministic, we're getting two very different accumulations, but bringing in the ensembles, we start to see that maybe the deterministic is at the upper end of this ensemble spread. We get that probabilistic information. We get more of a varied or spread outcome from the models, and this allows us to make a better decision on how we want to adjust things or communicate to the public. This is just an AR scale forecast. The plume diagrams on the left of IVT showing that control is at the upper limit. The control is related to the deterministic. If we look at each individual ensemble member, yes, the control is at the upper end, but almost all ensemble members are predicting AR3 or greater conditions over San Francisco, over the coastal Sonoma County. So we are looking at a high probability of a strong atmospheric river, but the control is likely at the upper limit of that ensemble spread. And that's when we move on to some of the precipitation forecasts and looking at the watershed mean aerial precipitation, seeing that the EC is favoring higher precipitation accumulations over the Northern California, and the GFS is favoring more central, or say Yuba Feather southward, just because the GFS is moving things further south quicker, but also holding things there versus the EC further north. It shows up in the time series of GFS. We know that the GFS deterministic is likely at the upper limit, but if we look at the ensemble spreads, it tells us a better story in terms of the GFS deterministic is at that upper limit. And this allows us to kind of work this into how we want to adjust forecasts. And again, it culminates in making those adjustments in the CNRFC has our QPF, and or during a briefing, being able to communicate some of those uncertainties and speak directly to the user of some of these forecasts. If it is the RFC QPF, that gets passed to the hydrologist, who then make a the hydrology forecast on the rivers. But knowing that there still is a lot of ensemble spread and the deterministic products are quite different from each other, we are able to say that confidence is quite low for a given forecast, and that information is also useful for a user. That's all I had, Julie, so I can pass it back to you, or we can move on to the next presentation.
I was still muted. Thanks, Chad. Let's go ahead and pass it along to Brett again.
All right, let me share my screen real quick. All right, I only have a few slides here, so my talk's going to be pretty brief. Generally wanted to just go over how we produce ensemble forecasting on the hydro side of things. And I thought I would just talk about mechanically, how we do that. There are essentially two big steps in ensemble forecasting on the hydro side. Number one is, and I mentioned this in the talk earlier this morning for those that attended that, there's sort of an uncertainty sort of parameterization process that goes on offline outside of our operational system, where we're building those relationships between forecasts and observations with temperature and precipitation for all lead times for every watershed that we model. And so when we come up with those comparisons and parametric distributions, we then use that information to sample likely scenarios of precipitation, temperature that get fed through our hydro modeling and generate ensembles of streamflows. To the left here is a screen capture of our CHIPS modeling net framework forecasting sort of window. And so the first step in our forecasting process on the hydro side of things is to generate our deterministic forecasts. So, in the morning, we're QCing all the observation networks that I talked about before. We feed that into the CHIPS modeling framework. The HEFS forecasters are generating the precipitation forecasts. Temperature and freezing level are brought in as well. And we go through each forecast group. So it may be hard to see, but we have a number of different forecast groups that we run through. We have two forecasters that typically work on those, sometimes more depending on the severity of the event that's going on. I did an expansion on the Russia Napa, so obviously you see all the different watersheds in the Russia Napa there. Once all those are processed, the hydro modelers have made their changes to the models and everything. We then kick off our ensemble forecasting processes. I should say that right before we do our deterministic forecast, we do some pre-processing on the meteorological ensemble side of things. So the generation of the precipitation ensembles and the temperature ensembles gets done really about the same time, or maybe even a little bit before the deterministic forecasts are done. But we don't kick off the hydrologic ensemble forecasting processes until the deterministic is done, because all the initial states and all the assumptions that go into the hydro modeling, they're done on the deterministic side, are also done on the ensemble side. So the same models, the same initial condition assumptions and everything are being used in the ensemble mode. So the ensemble mode is really done in a batch process. We're not going through every single individual location like we are on the deterministic, looking at it, making model changes. We assume that all the model changes that were made in the deterministic run are also reasonable for the ensemble mode. And so we just kick off basically a process that would just generate all the ensemble streamflow products for a particular forecast group. We have a number of servers in our office so that we can utilize, and so we can typically run about 4 or 5 different forecast groups in ensemble mode at a time. But in the morning we're running these ensembles going out 365 days. So it can take about an hour to really complete those morning HEFS runs. The other periods within a day, if we're in flood forecasting and we're going around the clock and ratioing them at 9 a.m. and 3 p.m. and 9 p.m. and 3 a.m., those other non-morning runs, we truncate at 30 days because really it's just the near term that we're focused on. And those take less, probably 30 minutes to run those. So, and when I say an hour for the morning runs, that's really from, actual computing the time series of the ensembles and also all the product generation that gets done and pushed to the website. Back to sort of that offline mode I talked about. This is just an example of, I think this probably the North Fork of the American. That's sort of our example case we always seem to show. But just this is an example of forecasted precipitation and observations. So, we utilize a pretty rich archive of forecasts and observations when we're parameterizing that uncertainty for HEFS. For precipitation, you kind of want at least 10 years. So the GEFS reforecasts, which we use the GEFS for certain lead times, really from day 7 through 14, we have, close to 25-ish years of those that we can use to parameterize the uncertainty. The shorter lead times in precipitation are based on the uncertainty in the CNRFC QPF. And we have roughly 14 or 15 years that we bring into that. So, so again, that's all offline, and all that's done once a year, sometimes twice a year, depending on what's going on. And then those statistical parameters are used throughout the water year to generate the neurological ensembles to get processed through the hydro models. And this is just our last slide that I have that I did also showed in the morning, just the ingredients of what goes into the streamflow ensembles. So again, I mentioned it before, the HAZ QPF is used as the input into the ensemble generator for precipitation ensembles for days 0 to 6 and 0 to 10 for temperature. And then after that, out to day 14, the mean of the GEFS is used to generate ensembles of precip and temperature for those longer lead times. Beyond 14 days, the meteorological inputs that go into the hydro modeling are pure climatology. So right now, I think it's 1980 to 2023 for this year. Next water year, we add another climatological year, so it'll be 1980 to 2024. And so that's what's used from days, it says 29, that's the error. Really from days 15 to 365 is pure climatology. So I think I'll just leave it there. Any questions?
Great, thanks, Brett. Any questions for Brett? And we'll have some more time for the questions at the end as well. Hearing none, then Patrick, I'll turn over to you to how you use forecast. Patrick, we can see your screen, but you are still muted.
Sorry about that. Can you hear me now?
Perfect. Great. Thank you.
Okay. Thank you for letting me know. I would have talked for 5 minutes and not known. So here I'm going to talk about how forecasts have been used in the San Francisco district. At the core, I want to emphasize that other core offices may take a different approach, but this is just how we've been doing it here in San Francisco. One thing important to note up front is that without temporary deviations to our existing water control plans for our 2 reservoirs in San Francisco, we really actually wouldn't be able to apply forecasts in the way that we've been doing it. So we have 2 reservoirs in San Francisco, Lake Mendocino, Lake Sonoma, and we have deviations to our water control plan that are allowing us to use forecasts to potentially retain some storage within our flood control pool. Here on this screen, you'll see a diagram for Lake Mendocino. The solid blue line is the observed storage. The orange line is the boundary between the flood control pool and the water supply pool. Under normal operations, any storage above that orange line must be temporary, and eventually we are compelled to evacuate that storage back to that orange line. That is what the existing water control plan requires for Lake Mendocino. However, with our temporary deviation, we've been allowed to potentially retain or release storage up to that gray line. Anything above that gray line, we would be compelled to release like our normal water control plan. But with this deviation, if there's any storage between that orange and gray line, we have the ability to retain that water if we want. And we are doing that using forecasts. So in water year 2025, the deviation at Lake Mendocino has actually allowed us to retain about 6,000 acre-feet of storage that we would have otherwise released if we didn't have a deviation in place. That 6,000 acre-feet total is based on the difference between the gray line and the orange line in about April. So you'll notice the storage has crossed that gray line recently. So right where that storage crosses, taking a delta between the gray line and the orange line is about 6,000 acre-feet. That's a rough estimate of how much water we've been able to retain at Lake Mendocino using forecasts. We also have a deviation in place at Lake Sonoma. The plot is slightly different because the boundaries are slightly different, but the key boundaries are the same. The orange is the boundary between the flood control pool and the water supply pool, and the gray line is a deviation that is in place that allows us to potentially store more water within the flood control pool. Here, we're just at that deviation threshold today. The delta between that deviation threshold and the water supply pool is 19,000 acre-feet. So because of the implementation of FIRO at Lake Sonoma, we're currently retaining about 19,000 acre-feet that would have otherwise been released. So between the two reservoirs in the Russian River watershed that we manage at the core San Francisco district, we're retaining about 25,000 acre-feet of water that would have otherwise been released if we weren't allowed to implement FIRO via these temporary minor deviations. So now I'm going to talk about or show you how those forecasts are used in real time to support the decision to retain storage instead of releasing. And really, it's about just kind of a daily process of reviewing all the available information. So here I took a screenshot of the internet browser bookmarks that I have. And typically in a daily process, you go from left to right, which is looking at the observed conditions and then looking at the available forecasts and making a determination if we're able to safely implement FIRO. So that's a screenshot. Now I'm going to navigate off this screen. And we're going to go to the internet to show you what I'd be doing in real time. So today, I'm looking at the observed forecasts or observed storage, excuse me, for Lake Sonoma. This is the observed storage for Lake Sonoma. So we're at 264,236 acre-feet. That is above the allowable top of water supply pool of 245,000 acre-feet. That's the 19,000 acre-feet of storage that I was referring to earlier. So now I have to answer a very basic question, which is it appropriate to be storing 19,000 acre-feet of water in our flood control pool? So now I'm going to go through the forecast to make a decision about that. So the first thing I would usually do is I would go to the QPF dashboard available from CW3E. We're going to look at the available forecasts for precipitation. And through the various weather models that we have available, it's pretty clear that this 10-day period is going to be pretty dry or dry enough to the point that, in my opinion, we'd be able to store that additional water in the flood control pool. The greatest amount of precipitation forecasted across the weather models is 0.2 inches across 10 days. Pretty clear indication that we have dry weather forecasts in the next 10 days. Looking at the forecasted inflow, populated the wrong one, so let me open the Lake Sonoma one here. The Lake Sonoma inflow forecast here across the 10-day period, the cumulative forecast across all the traces is about 200 acre-feet per day. That's pretty minimal since we're releasing about 200 acre-feet right now. So this is another forecast product that's supporting the decision to currently retain storage instead of releasing it. Then I'll look at the atmospheric river landfall tool that Chad showcased earlier. This is from day 0 to day 16. The last 2 products covered 0 to 10 days. I usually look at this product just to see what the 10 to 16 day forecast window is. And right now there's no activity being forecasted in the GEFS. And just to verify as well, I'll look at the European model to get some variety. And here, day 10 to 16, also no activity forecasted for the Russian River watershed. So here in real time, I've stepped through the process that we would do on a day-to-day basis just to see if we should retain or release water if we have that storage within that pool between the orange and gray line. Of course, right now is a period of dry weather, so a lot of these plots tend to be pretty boring, as in there's not a lot of activity. But it may be good to give some examples about what we'd be seeing during months where we do have activity. So let's highlight that period of January, end of January, early February of this year, where we had some potential wet weather, and we had to make a decision as to whether or not we were going to retain or release water. You'll notice from this plot for Lake Mendocino, here we were choosing to retain storage near that FIRO pool for the better part of the middle to near end of January. But then you'll notice there was some decrease in the storage where we opted to evacuate storage instead of retaining it towards the beginning of February. And that was because we were processing the available forecast information at that time, and we could see that there was going to be some increased inflow into the reservoir, and we made the decision at that point in time to increase our release. So here I'll just showcase some of the products that we were taking in at that time in January. So towards the end of the month in January, here's a QPF plot for January 25th. The plot at that time was showing, cumulative total of, a half inch to 1.2 inches across the models. On January 25th, we were contemplating what to do towards the end of the month, but we hadn't executed anything yet. And based on this forecast, we didn't really do anything. We were just maintaining our storage because we saw the potential for, but, we were going to wait a few more days to see if we need to take action. Fast forward to January 29th, which is 4 days later. The forecasts were evolving. It was clear that in the beginning of February, there was going to be, more precipitation. So that certainly led us to the belief that we should start to evacuate storage. We continued looking at the inflow forecast, which is taking that QPF and projecting inflow into the reservoir. So here we have the inflow forecast, cumulative inflow forecast for Lake Mendocino on January 25th. If you look at the cumulative forecast for that 10-day period into early February, the cumulative inflow was only ranging from about 1,500 to 4,000 acre feet. So on January 25th, we weren't too concerned, but fast forward to January 29th, 4 days later, looking at that cumulative forecast for, early February, February 4th, that forecasted cumulative inflow increased to a range of 2,500 to 14,000 acre feet. So seeing that change in inflow forecast, that prompted us to begin to release some storage from that FIRO space. We did not see a need to bring it all the way down to top of water supply pool or even below that because we didn't see any inflow forecast or QPF that would indicate the concern of the reservoir completely filling up. But we thought it would be good to evacuate some storage because it was pretty clear that that FIRO pool was going to be refilled, resulting from that storm. And for good measure, we also looked at the atmospheric river landfall tool as well during the period. So on January 25th, looking at early February, where the watershed's located about 39 degrees north, there wasn't a lot of AR activity forecasted, but doing our due diligence again, checking every day, we fast forward to January 29th, it was clear that there was going to be atmospheric river conditions in early February for our watershed. So that was further support to evacuate some storage instead of retaining it. So hopefully that walkthrough of how we were using these products in real time to support our decision making made sense. During our question and answer session, I'll take any questions that you may have.
Great. Thank you so much, Patrick. That was really great. I appreciate it. Brett did note in the chat, just for others, that he did have to drop off, but he's happy to answer questions. If you want to put them in chat, I can pass them along or reach out to him as well. We did have one question, I think it was from Sarah, even though it says Kyle, correct me if I'm wrong, about how to interpret the dprog DT tool on the CW3 website. Chad, do you mind taking this one?
Not at all. Seeing the screen okay?
Yeah, can you make it a little bigger? Maybe it's just small on my screen.
Yeah.
Perfect.
So
Thank you.
this, yeah, no worries. This dprog DT web page is essentially just a change in forecast from run to run or over time, and allows you to scroll through how the landfall tool is evolving from run to run. It goes back 7 days. The values in the slide bar at the top just give how many hours prior to right now or the latest run it was initialized, and the initialization is in the top right. We can see that the model runs at the far left are the runs initialized at 12 UTC on the 16th of April, where if we go all the way to the right, it's 12 UTC on the 23rd. I'll scroll through the top, the 150 threshold, just to show that you can step through and see if things might be trending north when things showed up, if they've gone away, if they're trending a different direction, and or the probability of AR conditions is increasing and or decreasing over time. We can see at the forecast initialized at 12 UTC on the 18th of April, we had decent probabilities of AR conditions over, or not AR conditions, but IVT greater than 150 at the 7-day mark. And if we step through, we can see that there's a lot of run-to-run variability, model run-to-model run variability. We increase to over 80%, and then things trend down. So we kind of fluctuated there between 7 and 4 days, but then it dropped off after that. How was that? Any other questions regarding the?
No, that's great. I just wanted to make sure. This is Kyle on the line. The part that I think threw me is that the dates, while it's the same 7-day range, slide through time.
Yes.
And that's what I wanted to make sure I understood correctly.
Yeah, so the validation, or like, yeah, so it's all, yeah, the x-axis here does change throughout each image. So to keep that in mind, that if you scroll through, it's like these blobs are just getting closer and closer to now, are coming closer to the coast essentially through time. But that's what dprog DT means. It's just a change in prognostics over a change in time.
Okay, great. It's very similar to the tool I use. I'll put that one in the chat, but just different enough that I wanted to make sure. I appreciate that.
Awesome. Yeah, no worries.
I also put it in chat. I thought, as I mentioned, I thought Patrick did a great job, and it was really wonderful to hear from him. But in this essence of learning from each other, are there others' thoughts on how they use observations and or forecast in water management that they would be willing to share with the group? Andy?
Hey, Julie. Are you able to hear me okay?
Yep, sound great.
So I don't know how much this has been addressed so far today because I joined late, but wanted to pass along that in Portland District, we do quite a bit of a longer term forecasts using the River Forecast Center's ESP ensemble. So I also know there was a, kind of a section looking at HEFS this morning. The ESP also works kind of the way that Brett outlined it, where after the model adjustments are made during their daily process, there's some period of time, either 10 or 15 days, depending on what the initial forecast is comprised of, where they're using their normal CHIPS forecast that uses the weather forcings, precipitation and temperature. But after that time window, they adjust to I think right now it's a 42-year climatology for the precip and temperature. So just climatology of what, range of things that had happened on that day. all the way out to, I think they go out to 18 months or 2 years or something. So what we do is we ingest the ESP traces. Currently, we have 2 ways that we could run that. We can either run the full ensemble, but we don't typically do that because right now that adjusting it to meet our operational constraints is too much manpower for us. So instead, we pre-process the full ensemble to yield 3 traces, which represent sort of like the 25th, 50th, and 75th percentile exceedances within that ESP ensemble out to the end of the calendar year. And we run that through our Willamette and Rogue ResSim watersheds. And we use that to make decisions on when we're going to do certain operations that we know are required for Endangered Species Act compliance, to coordinate maybe lowered flows if we think we need some, to plan for deviations if we think we're going to need a deviation. We did that this year, actually, to help us out, where we had 2 reservoirs in series and we stored above the rule curve for a while on one, kept the other one lower with the idea that we would rebalance them later. We didn't end up doing a formal deviation for that. Our division office coordinated with us and said they were comfortable with it without a formal deviation. But that modeling process lets us know, and it gives us an idea of how to plan things months in advance for our 2 reservoir systems that we operate.
Thanks, Andy. We hadn't talked about the longer lead time, so I think this is a great conversation starter. And tomorrow I'll have some feedback, and maybe this is a topic for this technical group to dig into more, as these longer lead times for forecasts. So thank you.
Yeah, you're welcome. And I know there was maybe some conversation about low elevation snow. I wanted to say that that's actually a big gap for us as well, and particularly in these longer lead time models. They're really highly dependent at this time of year on the existing snow state. And to the extent that we don't know as much as we should about the snow at lower elevations out in the basin, that provides a significant amount of uncertainty for that process.
Noted. Patrick, there was another question for you in the chat about the physical and regulatory constraints on releases. How much lead time do you need, or how much will you allow encroachment into the deviation pool?
Yeah, I'll be happy to answer that question. So, one of the important components of our deviations and subsequent water control manual updates is defining that pool for which we would allow ourselves in the Corps to apply FIRO to potentially retain storage instead of releasing. It's important to note that we're not opening, or at least in San Francisco, we have not opened up our entire flood control pool for this type of application. It's been for a very limited amount of storage in that pool. At Lake Mendocino and Lake Sonoma, we've allowed ourselves about 11,000 acre-feet of storage to be able to do this. And that storage threshold, or that storage amount, was not just some, let's say, random amount picked out of thin air. It really had to do with our ability to release water within a certain amount of time frame in a reasonable manner. So, the amount of lead time that we would need to release 11,000 acre-feet, for example, if we had to, we could do it in one day. That would be like the emergency off-ramp. If the forecasts were completely just surprising us at the last minute, we could clear that storage in one day if we had to. But that's not something we want to do. We want to be able to do things with, probably 2, 3, 4 days of lead time. And that's what we've been able to do with the forecasts that are generated in the Russian River watershed. Obviously, there's a lot of variability, many days out, but that variability tends to, let's say, decline within the less than 5 day period. And within that less than 5 day period, we're able to manage 11,000 acre feet pretty reasonably. Releases out of Lake Mendocino and Lake Sonoma typically range from 1,000 to 4,000 acre feet. So if you hold that over a 24-hour period, that's ranging from 2,000 to 8,000 acre feet of volume being released. Our FIRO pools are 11,000 acre feet. So those are volumes that can be managed over a period of a few days with a few days of lead time. If we had more lead time and more reliable forecasts, then we can probably manage more of a FIRO pool. But based on what we have today, I'd say 11,000 acre feet is what's reasonable.
Don, do you have additional comment?
Yeah, I just had a question for Patrick. This is Don Seymour, Sonoma Water. But Patrick, with Lake Sonoma, it's a little different because the FIRO, deviation pool does vary with season a bit. There's some seasonality to that pool. So what goes in the thought process of just the release? It's also probably the likelihood of storm events as we go further into later into the season, right? Wouldn't you agree to that?
Correct. So in the summer at Lake Sonoma, we're managing a FIRO pool now of 19,000 acre feet. So if for some reason we had to clear 19,000 acre feet, we would have to have probably an additional few days of releases in order to do that. The likelihood of having some sort of need to bring the pool back down to the top of water supply pool in April, May, or June is very low. So the ability to manage 19,000 acre feet in this period is a lot more doable than in the winter, given the current lead times that we have for forecasts. We also can't go completely crazy and say, hey, let's open up the whole pool in the summer for FIRO, simply because, at Lake Sonoma at least, because we do have to draw the reservoir back down to the winter levels at some point. And if you go too high at Lake Sonoma, you're going to have to artificially release storage in the fall to get it back down to those thresholds. And that would be causing concerns for us in terms of our environmental constraints, in terms of the fisheries in the watershed. So, but it's a good point, Don, about the differences between managing FIRO in the summer versus, let's say, the winter, where we have a lot more activity and a greater need to potentially bring the reservoir back down to the water supply pool.
Thanks, Patrick.
So, hey, Julie.
Yeah.
This is Chance. I could give an example of how we used ensembles in ResSim in 2023, if you're interested. So.
Yeah, that would be great.
So, in 2023, we had a large snowpack. Many reservoirs in the San Joaquin system at least some reservoirs were encroached through no fault of the operators, just a function of the weather and how the reservoirs filled, and then how another event came in. And so we got a request internally to look at using ensembles to figure out if there was going to be a situation where there's going to be an induced surcharge operation out of New Don Pedro. So I built a ResSim model that covered the whole watershed, and I coordinated with TID. And of course, TID is coordinating with the Corps of Engineers, and they're all very aware of all their operations and how they're going to operate the project. So what the product I developed was just an additional information for the operator, being TID. And so I built a ResSim model. We used daily ensembles on a daily time step that were provided by the Weather Service, but I could run ResSim on an hourly time step, which is what I did. But we basically ran all those ensembles through and looked at what the risk would be, because TID was constrained by how much water they could release, based on water control manual requirements. And so we ran the ensembles through and said we looked at when there could be an issue or when there could be an induced surcharge operation. It was useful because we did it towards the end of March, early April. And as we did these simulations and ran them once a week, what we found was over time, we were able to communicate to them over time, just, the risk of having an induced surcharge operation went down. And it was just additional information that we shared with them, and they found it useful. So that's a particular instance where we used ensembles. So, and I could also see where if there was a rain flood event, rather than a snowmelt event, a rain flood event, and projects were encroached and got into a situation where they can have an induced surcharge operation. I really like the Weather Service's 30-day hourly ensemble products that they produce, because those give you a little bit more resolution on the hydrograph, the inflow hydrograph and local flow hydrographs downstream, and can give you an idea of the impacts of what short-term operations would be longer term in terms of maybe filling and spilling or having to run an induced surcharge operation because the reservoir is getting too full. So anyways, that was very useful. So, and ResSim's a great tool to use, and the ensemble products that the Weather Surfer puts out are great. And we're doing more with that internally in the RCRU, where, in Kale's group. So anyways.
Great. Thanks so much for sharing, Chan. I saw Olivia was on the line, and because you mentioned TID, I didn't know, Olivia, if you had anything else to add, and I realize I'm putting you on the spot, so don't feel free to say no, but I just wanted to give you an opportunity.
Yeah, no problem. I mean, for us, we've always kind of leaned towards using ensembles just because it gives you the ability to make more risk-based decisions rather than that more deterministic value where you are going to take on some risk in one direction or the other. We've always liked to use both RFC products for ensembles and use them in comparison to our own internal models. And a lot of times we work through like almost a weighting system between the two, because on occasion, sometimes we have similar volumes, yet they come off at different rates. And sometimes RFC has faster rates, sometimes our internal model does. And, as you're looking through the forecast in enough years, you get a feel for what's the likelihood of that, and you can weight one over the other. So that's a way in which that we've found a lot of use. And even this year, working with the Corps, where we've been able to stay encroached within the flood control space because we are experiencing that faster rate of runoff than we typically would have in the past. And the way that our flood control manual was built for a much later average snowpack runoff.
Thank you. And I would like to thank our presenters again. So big thank you to Ava, Brett, Chad, and Patrick. So appreciate you guys talking about your experiences and the forecast and observations. So thank you. And to Andy and Chan, and for the questions in the chat. So thank you everyone for contributing to the session. I'm going to go ahead and turn it back to Joe to take us on to the next part.
Great. All right, let me share my own set of slides here. Can you guys see that okay?
Yes, looks good.
Okay, awesome. All right, so thanks, Julie. Yeah, and the presenters and speakers before me, thank you for a great session there, a great topic of observations and forecasts and sharing your knowledge and experience there. What I'm going to be talking about now is how viability assessments, the FIRO viability assessments, can support water control manual updates. I'll probably say it multiple times throughout my portion here, but I'll go ahead and lead with it and say that really the ultimate goal of all of the FIRO pilot projects that have been started and went underway and completed, and the ones that are going to be started, is to realize potential changes in reservoir operations that could deliver the water management mission as best as possible at the various reservoirs that are being assessed and evaluated for potential FIRO implementation. So it's important that the setting up and the development and the work performed on these viability assessments are done so with that in mind. So that way it can support and inform water control manual updates to the best that they can. So that way districts and divisions can use that information as best as they see fit to make their lives a little bit easier whenever it comes to them doing what they're required and charged to do, which is obviously real-time water management, but update where appropriate water control plans and contained in those water control manuals. And so these viability assessments are hopefully as useful as possible to help the Corps with that. I'll go over these first few slides a little bit quickly because I've given some of these slides in other contexts before, but I really want to start off by connecting the USACE water management mission and the FIRO pilot projects and the viability assessment work that's been done, and reminding ourselves that the main reasons for why what the Corps does when it comes to water management and why it does those things is making sure that the projects are operating to its authorized purposes, that the integrity, both operational and structural, is maintained, and then avoidance of avoiding risk to public health and safety, life and property, all of that stuff that I think a lot of us already know and assume that that is why the water management teams exist, is to execute this water management mission. And whether it be for Corps of Engineers owned and operated projects, or it's for projects that are regulated by the Corps of Engineers but owned and operated by other entities, more often than not, we come across those and label those as Section 7 projects. The prescribed rules and regulations for how to operate those reservoirs for water management is found in the Water Control Manual, and the plan or the operating rules exist in the form of what's called a water control plan. And the process that a district or division goes through to update a water control manual is not a short or simple one. It's got a lot of moving parts that are interconnected, and whether it's engineering in nature, or it's more regulatory, or it's related to endangered species or NEPA, there's a lot of things that districts are needing to balance and juggle and satisfy, and there's not, for a lot of this flow chart that you see here, there's not a whole lot of wiggle room of or discretion on what a district does, or what a district can forego or set aside. Like, a lot of these things are required based off of law, regulations, statutes, things like that. So where on here can the outputs of a FIRO pilot project fit in? Where really does this this viability assessment work? Where does this fit within this structured framework of updating a water control manual? And we'll talk about that a little bit here in a few minutes. But to remind ourselves of what FIRO is all about, I'll leave this definition on here that was submitted to AMS a few years ago. And really, at the Corps of Engineers, the goal of pursuing FIRO is using the forecast and observation information. We're trying to find a better balance between the multiple, or it could be a single purpose, or it could be multiple authorized purposes at a project, of just finding the best balance between the authorized purposes without negatively impacting the purposes at that project. Now, out in the West, the primary purpose at a lot of these Corps projects are flood risk management. And so regardless of whether or not the objective of a FIRO pilot project is flood risk management, it goes without saying that whatever is being investigated or considered to be changed, it can't negatively impact flood risk management. And really, it shouldn't be negatively impacting the other purposes either. So it's kind of an interesting threading of a needle that needs to happen here. Like, can you do things better without messing everything else up? And that's what's been contemplated for each pilot project that's been pursued. Now, the way that we go about looking at the potential implementation of FIRO concepts is in this framework of a viability assessment, like this viability assessment process that has been developed and adapted and massaged and evolved over time with each pilot project. Because you're wanting to, with a pilot project, since it is an R&D effort, you want to use that space or that sandbox to creatively explore new ways to use the best information available. And you want to see how those new scenarios and strategies, how they would perform when compared to the existing or baseline water control plan for our project's water control manual. Starting with Lake Mendocino and then fine-tuned for each pilot project afterwards, within the FIRO program, this viability assessment framework was developed, and it's come down to a repeatable process, and there is quite a bit of similarities, quite a few similarities and overlap between the viability assessment process and the already existing Corps of Engineers feasibility study process. They look at similar things, they do similar things. It's not like the viability assessment process isn't required to adhere to core policy in the same way that a feasibility study does. But the reason why the feasibility study process is the way that it is because it's thorough, it's robust, and it produces trustworthy outcomes, and those are the same sorts of things that we want the viability assessment work to do. And so naturally, they kind of end up overlapping and covering a lot of the same ground. This next slide, I'm going to show the 10 viability assessment steps that goes into a final viability assessment that's performed for FIRO pilot projects to date. I won't belabor these too much because a lot of you have either worked on viability assessments, some of you may have worked on feasibility studies, maybe some of you worked on both, but I just wanted to at the very least go through each of these so that way you can see the complete picture of start to finish, what does a viability assessment look like, and a little bit of detail of what feeds into each step. So you start off by identifying what are the objectives of this specific FIRO pilot project. Are you looking to improve flood risk management outcomes, water conservation, hydropower, environmental related outcomes? It's got to be more than just a vague improve performance. There should be more detail, more specificity, and the objectives should be quantitative. So then that way you can actually measure and grade whether or not those objectives were achieved as part of the effort. So and part of making sure that you're playing within the bounds that you should be, you need to be defining and establishing your constraints. They could be physical constraints, like how tall the dam is, how much water can be released, so on and so forth, like that. Could be regulatory constraints, constraints that are imposed by agencies like the Corps of Engineers, Fish and Wildlife Service, things like that. And they could be related to the environment, to dam safety, to flood risk management. But these constraints are things that cannot be compromised within the water control plan alternative comparison work. So these are the non-negotiables here. Then moving on, you need to be identifying the performance objectives. So what are the specific ways that we would be, where we can tell if we're achieving the overall FIRO objective for the project. So you may be looking into, if it's more conservation related, you could be looking at what does the maximum post-wet season refill, how does that performance look under these new scenarios? Are you looking to maximize power generation? And because hydropower was identified as one of the FIRO objectives, you need to be identifying more specific performance objectives that then can be measured and that you can associate performance metrics to. So if you're looking to maximize power generation, what are the metrics that are associated with that, so that way you can tell whether or not you actually are maximizing power generation or not. Or if you're looking at how often, like the frequency of which certain pool temperatures are being achieved for the support of like fish species and things like that. So all of this is like pre-work planning of identifying objectives, constraints, and metrics. Then you move into building the candidate water control plans. So you need obviously a baseline or existing operations one, and then a number of other like FIRO water control plans. It can be ones that don't involve FIRO as well if you want to make those sorts of other comparisons, like with and without forecast, if that's valuable to the effort. But this is the fun brainstorming part of figuring out how you can tweak different knobs of the existing operations and see what if you use this information, what if you change the timing, what if you change the storage amounts, things like that. And that is done in kind of like almost two different stages, where we've traditionally had a preliminary viability assessment and a final viability assessment, where the preliminary viability assessment, or PVA, is very exploratory and testing things just to see what breaks the system. And then you do a more intentional, greater detail work in the final viability assessment, where you're really honing in on the potential water control plans that have a chance of being implemented. You know, so you're spending time on stuff that actually could be useful to a district to consider. After that, you also need to have some way of accounting for the water within this framework, in conjunction with the reservoir operations models that are being used for simulation. You want to make sure that you know where and how much water is, where water is going, how much of it is going there, to meet the various like demands, objectives, and things within the system. So that way you can show that complete picture as you're going through the simulations. And so the simulations that you're going to do are going to follow the simulations plan that you develop. Oftentimes we've looked at a couple main pieces within the simulation plan, looking at some version of a period of record simulation, as well as using scaled events, because oftentimes within the period of record, which can be 30 years or more, it may not capture large enough events for you to see if it's like really stressing the system or performing the way that you want to see if it can perform. And so the period of record is a good starting point to use, but also scaled events is another useful tool in that way, in the way that it will allow you to evaluate events that haven't happened but are large enough to test the water control plans and the alternatives that you develop, to see whether or not the performance being measured is sufficient or not. So as you're simulating the performance of the various water control plan candidates, you're using the scaled events and the period of record events, you're going to be then looking at how the various outcomes are similar or different from one to the other. And you're going to be comparing those alternatives and the results of those alternatives. I kind of breezed through number 8, and I think if you probably ask Rob or someone that does that's done a lot of this work on various pilot projects, is that number 8, depending on the pilot project, might be the longest portion, because if you're doing a whole lot of simulations and then you realize that something in the model needs to be tweaked, you need to run the simulations again, and then, oh, this needs to be updated or corrected, and you have to run the simulations all over again. And so it stresses the importance of doing as much work ahead of time through 1 through 7, so that way you can minimize the amount of redos that need to be done in step number 8. It still can't be completely avoided, but it can take a lot of time, especially if the system that you're evaluating is really complex and the run times for the simulations are long. So going through step 8 can take a pretty long time if there's tweaks and changes that are identified that need to be made along the way. And so using those performance objectives and metrics, then you're comparing the alternatives to see which ones are doing better at achieving certain objectives than others, and you're using the metrics to help you show that. And then that comes down to recommending a path forward. And it's important here for me to reiterate that the water control manual update process is a Corps of Engineers process that is executed and managed and stewarded by the district and division offices. And so that is completely run and appropriately in charge by the district and division offices. And these are, and the recommended path forward would be just that, a recommendation from the steering committee that was formed for these pilot projects that kind of puts these plans together. It's not some sort of binding agreement that the district or division offices must now incorporate a recommendation, but since offices are involved in part of the steering committees, hopefully there's some synchronization there that what's being recommended is something that is accepted and palatable to the district offices. And it's also important, I think, from a pilot project to give it validity, that the steering committee and its viability assessment does recommend something, and it doesn't just look like a whole bunch of fun work that was done without some sort of conclusion that came from it. So these 10 steps has been, or the viability assessment process can be boiled down to these 10 steps, and essentially these 10 steps is what's been done at pilot projects so far. And you can see on this diagram here where the viability assessment fits within the overall pilot project process. So you can see that when you're starting with the steering committee, then you develop the work plan of what work's going to be done, and then the viability assessment is when the work is actually being executed. And like I said, with the intent that it informs and supports a potential water control manual update. And something that we're going to talk a little bit more about tomorrow that I at least wanted to mention quickly here is that water control plan deviations are used as part of the viability assessment process to test out the likely recommended FIRO scenario or scenarios, and to allow for district and reservoir operating partners to gain operational experience with implementing some of those FIRO concepts. To date, the durations of some of these deviations have been up to 5 years long, and that's really to help span the gap of completing a viability assessment and completing the pilot project work, and or potentially spanning the gap of completing a FIRO pilot project and then updating a water control manual. So the improved performance in whatever way it's being measured and characterized is in some version in place and being utilized to see real world benefits, that those are being done in the meantime while the final documentation is being finished and concluded. I'm not going to go through this slide in detail, but I wanted to show some cool stuff as an example that the Sacramento district has done, where they've even identified, since they had a water control manual project and a FIRO pilot project going on at the same time, they broke down the different pieces of each of the processes and then identified when certain pieces of information was shared from one to the other. And the alignment of especially concurrent water control manual update and FIRO pilot project work is extremely important, so that way you're not like redoing things, undoing things, repeating things later on, and trying to be as efficient and effective as possible with the limited time, funding, and other resources that are available to do this work. So I wanted to show this as an example that regardless of what the district constraints or opportunities there are for pursuing FIRO and updating a water control manual, that it's important to find to do some version of alignment between the two efforts or integrate those efforts, so that way it's done without wasting time and money, which is, when you're doing something new, it's hard for that not to happen. And so the more that we can minimize it, the better. And then the last thing I wanted to highlight was to go over some viability assessment pathways. And so these pathways, through experience with these pilot projects and knowing that not every reservoir within the core portfolio is going to have the opportunity to stand up a steering committee and do a viability assessment and then update a water control manual, that there's different versions or different pathways of a viability assessment that can meet the needs, the specific needs of that reservoir, of that district at that time. And so through the experience of those that have worked on various pilot projects, we kind of developed these pathways that fall into 3 different categories: an expedited viability assessment, a streamlined, and a full viability assessment. Starting with the last one, the full viability assessment is essentially what has been done at the pilot projects, like exactly what we've just been talking about. But if that option isn't available to a district, then there are, for different reasons, different constraints, whether it's timing or funding or whatever, that there's other like shorter, quicker versions that could still provide some, if not a lot, of benefit to a water control manual update, acknowledging the constraints that need to be worked within. And so the expedited one, that would be appropriate for sites that have very few or very low barriers to FIRO, and would be the least resource intensive one and would be the quickest to complete. And so you may have the ability to utilize existing reservoir models, decision support tools, and other forecasts that are familiar to the water managers, to where you don't need to create new data sets you can use, or tools you can use existing ones in order to implement FIRO. And so this would be more appropriate for where you might just be looking at one reservoir, or the effort would be more straightforward. The streamlined one would be like halfway in between, where it's a little bit more straightforward than needing to figure everything out. That would be done with a full viability assessment, but there still is some unknowns where it would take a little bit more time and effort to work through the complexities of the project in question. So the data and models may be adequate, that might need a little bit more tweaking. There is some willingness among the parties to overcome challenges, and the parties would be both the Corps and the reservoir operating partners. There would be a little bit more exploration needed to figure some things out, but not so much so that it's going to take as long as a full viability assessment would take. a work plan for a streamlined viability assessment is beneficial, needed, and required, but maybe the work anticipated isn't so much so to where like a preliminary viability assessment would be required to test out where things break, and that like preliminary step could be skipped and could go into like the final viability assessment, where you kind of already have an idea of which alternatives, types of alternatives could be implemented. So this is something that is newer. This viability assessment pathways idea is a newer development within the FIRO program, and we're looking to get this information out there to everyone in the form of guidance documents here later this year, if we can. So that's I wanted to share that, as this is not this isn't a finalized guidance document, but it's something that we've been working on for months, that hopefully in the near future that we can provide in more detail to everyone. So to wrap up, I just have a few more bullets here where I wanted to highlight and reiterate that the viability assessments done within a FIRO pilot project, that's a framework where FIRO concepts can be developed, explored, and evaluated for the potential inclusion in future water control plan revisions. And the ultimate goal of a viability assessment is to inform and support potential water control plan revisions and water control manual updates. It's not just for the fun of researching stuff. It's actually for making it useful in the real world. And then based on the experience gained from the pilot projects to date, the viability assessment pathways that I was just talking about, they've been developed in a way that where there's options available that can best fit the specific needs and constraints associated with supporting a water control manual update. There's not just a one-size-fits-all, you must do it the way that it was done for Lake Mendocino. We're trying to make things as adaptable as possible, so there's always options available to districts for pursuing and considering and potentially pursuing FIRO. Okay, I had a full screen going, so I don't know how many questions, if any, were asked. So I'm going to stop sharing this for a second, so that way I can actually see that. Thank you for your time, everybody.
Thanks, Joe. Joe, Patrick said he has 2 more minutes of topics to cover, but I think we should address any questions from your presentation first, and then Patrick, we can turn it over to you.
Great. Yeah, we can get to you, Patrick, here in a second. Any questions or comments on how viability assessments can support water control manual updates? Okay, I'm not hearing anything right now. Feel free to add anything to the chat, or you can reach out to me later as well if something comes up that you're curious about after we wrap up this afternoon. But in the meantime, Julie, we can go to Patrick if you wanted to add your 2 extra minutes of how you're using forecast in San Francisco district. Feel free.
Thank you. I realize now that I had 4 PowerPoint slides prepared. I went through the first 3, and then I kind of just cut off myself on the 4th slide. So I'd be remiss to not cover that topic, which is just so earlier I was talking about how I use those forecast products as largely a kind of qualitative assessment. I wanted to touch on the available hydrologic modeling that we can do internally in the core, more of a quantitative assessment. So we have our core water management system model of the Russian River watershed that we have available for Lake Mendocino and Lake Sonoma. So we're able to independently pull in our own precipitation grids and develop our own hydrology. and route our reservoir release decisions through there. I want to thank the HEC staff for the help they provided to us in recent years, because we had some issues with that model setup, and recently they've been helping us get that model stood up. So we have been able to use that model this water year, and that will be very useful moving forward. We also have what we call the Lake Mendocino Decision Support System, which is a web-based ResSim tool that our local partner, Snow and Water, is helping us stand up. It's a tool that we also have available to import our reservoir release decisions and route flows to the key downstream point locations. The two models both utilize HC ResSim, which is the Corps' official reservoir simulation system. So that's good. The differences between the SWIMS and the Lake Mendocino Decision Support System. SWIMS, we're using a different routing method. That model is using our modified poles routing method versus the Decision Support System, which uses the lag and K routing method consistent with the Weather Service. So we have those two models available to evaluate our release decisions when necessary. So if we're trying to release in a scenario where flows may be high downstream for periods of time, hydrologic routing is a really important thing to consider when you're making a release decision. In other instances where we're releasing into blue sky conditions, it's less important, but still good for us to have those tools available if we want to evaluate our release decisions. So I thought it would be important to note that, since I had prepared a slide and was going to talk about it and did not. So that's the additional 2 minutes I wanted to just cover for today.
Great, thanks, Patrick. Okay, so in these last few minutes, we'll wrap up this first session of the FIRO Technical workshop that we got kicked off today. Julie, is there anything that you want to bring up here to start off the wrap up?
I just want to thank everybody for joining both the pre-meeting workshops and the 101s, and then today. I appreciate, again, everybody doing the presentations and also the feedback and the conversations that we have had, and hope that continues tomorrow. We've had some questions about where the recordings and slides will be, and I think Joe and I need to tag up on that a little bit more, but hopefully we'll have something to share at the wrap up tomorrow, and we'll let everybody know where those will live to access them beyond this meeting.
Great. Yeah, and I was trying to keep tabs, Julie, and I think we were in the mid 30s to low 40s in terms of attendance for each of the pre-workshop sessions this morning. So I think there was almost a 50-50 split actually between the two. It looks like it was about the same. So yeah, thanks for everyone for participating in those today. And tomorrow we're going to get started with the second session, looking at HEC tools and how they have been and can be used for FIRO work. And then we'll have a break for lunch, and then in the afternoon we've got a few topics that we're going to be talking about. We're going to have Aquavale give a demonstration on the work that they've been doing with like water management, supporting like dashboards for real-time operations. And then we'll have a little talk about, I mentioned water control plan deviations. We're going to be talking about that a little bit so everyone gets a flavor of a version of what that process looks like for getting a deviation requested and then approved. And then we'll talk more about some ideas from us and from you guys on what the next webinars and trainings and next steps will be looking like, because we don't want to just have this be like a once in a long while type get together. We want to maintain this community and these conversations multiple times a year, so that way we can keep everyone informed of how things are going and what new developments there are. And so yeah, please don't miss those 2 sessions tomorrow. That's going to be important stuff that we'd like to cover with you guys and hear from you guys on. Okay, that's all the talking I wanted to do. So, and Julie, unless you have anything else, I think we can wrap it up.
Great. We'll see everybody tomorrow.
Yep. Thanks, everybody. Have a good rest of your day.
Thank you.
Thank you.
Thanks.
Thank you.